Okay, so we're going to start 2.9 now. We've got about 20 minutes to knock out as much learning as we can do. And we're going to put in our best effort, right?
So this some different
That's
stuff?
what I'm talking about.
Always and forever.
This
Always
some-
and forever.
This some different?
No.
Say again.
This some different?
This is, so I'll explain in a second. Let's look at our
So this
objectives.
ain't this. This ain't this.
No, it is not roots. So we're still learning about continuous and discrete functions and linear and exponential. We're still learning that. So here's our objectives. Donovan, can you read our first objective for us, please?
I can show equivalency between different equations of the same one.
This might be a slightly new term. Do y'all know what we mean when we say equivalent?
Yes, different but the same.
Different but the same. They're not quite equal. Let me show the slight difference here.
And they got 3 lines.
Yes, have I used that in this class?
Yes.
No,
So-
that isn't it.
You just
I
know.
haven't learned that shit.
So notice how these two things are equal. 3x is equal to 2x minus 4. Now is that always going to be equal? No. In fact, if I subtract 2x to reveal, hey, that's a 0, 3x minus 2x is x is equal to what?
-4.
The only time that these two things are equal is when x is -4. That's the only time they're equal. Does that make sense?
Okay.
Equivalency is something like this.
Different forms.
These two things are equivalent. They look different, don't they?
Very.
Yes, sir.
But if I distribute,
They come out and do the same thing.
what's -3 minus 1?
2.
-4.
-4. So are they actually the same?
They're equals.
That's the same exact thing.
They're exactly the same thing. They looked different, but they were the same thing,
They're
just in different forms.
different but equal.
So to get, you had to distribute it for it to actually equal.
Well, so here's one thing I want you to understand. This is just an algebraic idea of equivalency. Mathematically, there are a lot of different things that can be equivalent. Mr. Bloom's like, yes, I spent a whole class learning about how things could be equivalent, and I never want to look at all that again.
Never again.
There are lots of different things that can be equivalent. And this is actually a really important idea that I've only really started to understand until recently. But we can show how lots of different things are effectively the same while still looking somewhat different. So because these are the same, not only can we put the equal sign, we can put a third line. And if we show a third line there, it's saying, hey, they look different, but they're effectively the same thing. They're equivalent to each other. Okay, and so we're going to use that because we're getting into this objective now. Brady, can you read our second objective for us?
I can use the point, slope, and slope-intercept forms of linear equations to create accurate algebraic representations of a line.
Okay, so you've actually seen these equations before, point, slope, and slope-intercept. I have not actually used those terms yet in class because I wanted you to understand where they came from. You've been using them since last unit. You've heard those terms since you took Algebra 1. Now we're going to start to pair those two ideas together, and we're going to create algebraic representations. What do I mean by an algebraic representation, though?
Algebra.
Thank you.
Yeah, that's about all I got.
That's it? Okay, well let me ask you this. Would this be an algebraic representation?
No, that's a graph.
That's a graphical representation. Is this an algebraic representation?
No, it'd be an equation.
Oh, there we go, right? When we say an algebraic representation, I'm just talking about an equation, and an inequality, and expression. That's it. But I need you to be aware of that. What I'm saying here is we're going to be creating the equations of the line. Mona, can you read our last objective for us?
I can create a graphical representation of a line given an equation. Hold on, given an equation with point slope or slope intercept.
Okay, so we want to also be able to create those graphical representations. That's a good question because there's lots of different types of equations out there. And so I don't want to just say, hey, we're just thinking about equations. And I also want us to always be thinking about this idea of representations. Graphical, tabular, algebraic. And so the other thing is that when I say an algebraic representation, it can cover inequalities. It can cover equations. It can cover expressions. And so if it's any one of those three, it's algebraic. And so I use that as an umbrella idea. Like that? Revisit there?
Yeah, I like the umbrella thing.
Me too. Okay.
That's pretty
So-
Gonna get wet.
Zach and Sion, we're working on predicting the number of quilt blocks in this pattern. This is 2.9. When they compared the results, they had an interesting discussion. So when I look right here, the first term, how many quilts do you see?
7.
7, right? So I see a 7 up here. For the second one, how many do you see up there?
14.
Do we all agree? 14?
14, yeah. That'd count.
I was guessing.
Now that's where we're on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Yeah, I think I only see 13. Be careful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. If you double count that centerpiece, you do get 14. But that's why it's important to count, okay? Next one,
I'm going to 1 to 6, 19.
okay?
Right now it's
19. Why'd you think 19, Braden?
Feel like counting.
Okay, you already went ahead and counted it? Okay, I didn't know if you'd already counted if there was a pattern that you noticed. So I noticed a pattern, or I assumed a pattern. So Zach said I got y equals 6n plus 1 because I noticed that 6 blocks were added each time, so the pattern must have started with 1 block at n equals 0. Sion said I got y equals 6 times n minus 1 plus 7 because I noticed that at n equals 1, the first term there were 7 blocks, and at n equals 2 there were 13, so I used my table to see that I could get the number of blocks by taking 1 less than n, multiplying by 6, because of all that, and then adding 7 because that's how many blocks are in the first figure. Here's my table.
Zach's first one.
What do you think about the strategies that Zach and Sion used? Are either of them correct? Why or why not use as many representations as you can to support your answer? If you need a separate sheet of paper, please feel free to grab one. But right now, I want you to take just a minute, maybe a minute and a half, to think on your own, and then I'm going to have you start working within your group to answer this question. If you finish number 1, guess what?
You're done.
No. Move on to number 2.
So do we start answering now or?
So yeah, if you want to go ahead and start answering now with number 1, go for it. I want you to think for a minute and a half on your own, and then we're going to start talking within our groups and discussing together. But yeah, if you want to go ahead and start writing something, let me know. Does anyone want a sheet of paper? I'll go ahead and bring it out. You can raise your hand. No? 1.
That be.
Got Donovan. Who else? Anybody else paper? Sure. Well, I'd probably keep my notes separate for different things. So I might do 2.9 on something else.
Blue ice cream. You ever been to the Big Bear, Mr. Kennedy?